So let me take that question. Yes, somebody is messaging me. Only people with having PC, personal computer, can have the record option available. So if there is anybody, please volunteer. I will be happy if you can do that. So we were here. So yesterday we tried to discuss about fluid dynamics, the different techniques, the different steps involved in computational fluid dynamics, namely trying to detail the flow physics with a set of equations, the equations being called as governing equations, mass, momentum, and energy conservation equations. And if there is any chemical reaction, then you may have to add species transport equation, which is conservation of species equation. And also, I told you, this sort of equations usually have a source term or a body force component involved, with gravitational field force or magnetic field force or such forces which are acting far away from the body, trying to influence the fluid physics is present. So we can always include this body forces as an additional source term in the set of equations. Then we try to understand CFD can only be used in relation with experiments, and you have to do some sort of validation or verification at the end of your CFD simulation. Okay. Okay. And then we were trying to understand the basics of grid generation. Here I told you the essence of grid generation is that computer can solve only discrete set of values, and the fluid physics equations, the governing equations as you see here, is mostly continuous functions in space and time, which means that the derivations or the differential values at all points should be available, okay, for the function. The function is to be continuous because the system is continuum and the field functions are continuous. But the computer is not able to hold all the information at all the discrete points. So here we have to uh, give specific information at different locations for the computer to perform the computation. So here you have to divide the domain into finite points, which you call as discretization or grid generation. I'm sorry, which you call as grid generation, which you physically divide the domain into distinct points from which computer can take the value for computation. Okay. So now in solid solid mechanics or finite element method, you have these discrete points being called as finite uh, points, which you can apply finite difference method. Okay, because you have finite points there. But unlike in solid state physics, the difference in fluid physics is that fluid doesn't have a specific shape, or it takes the shape of the container, or takes the shape of the region of space it is occupying. So there is always some volume, which is space in region of space through which the fluid is trying to pass. Okay. So here, more than finite difference techniques, we may include some control volume approach or region of space approach in studying the flow physics. So this is why a finite volume method is important, or it may be more accurate for fluid physics. Okay. This is where we stopped the discussion yesterday. And we also discussed that discretization is a technique that is used to convert the partial differential equations to linear algebraic equations. I'm not audible. Am I audible? Am I audible? To require a set of governing equations, right? To detail the physics. And I was trying to tell you what are the different types of flows that are commonly modeled in computational fluid dynamics. So mathematically, how to see the different type of flows. So this is where we left yesterday. So I'll just write. I'll just write. where we have left yesterday. So we so we discussed the different types of flows. Okay. And people are still joining. So we discussed about laminar and we discussed about turbulence. So here I told in laminar flow you have sheet-like flow. So the modeling is a bit easy. Here in turbulent flow you have chaos, or you need chaotic prediction, or you need a model which predicts chaos. So this is usually you need a turbulence model. So you need a model, turbulence model, if you want to simulate such flows. For laminar flows, it is pretty much easier to simulate. Then we discussed about irrotational and rotational flow. Irrotational and rotational flow. So here we understood irrotationality is mostly associated with inviscid. Okay, so the flow being inviscid. So here the flow being inviscid. Okay, so such flows are called as potential flows. Okay, irrotational inviscid flows are called as potential flows. So if you use a solver to solve your problem, you can see that you are able to select inviscid flow. Based on inviscid flow, you can detail the physics. It will ask whether you are simulating an inviscid flow. For rotational flow, you see that whenever there is viscosity coming into picture, I have already explained this. You have to model the flow with rotational flow physics. So here, Navier-Stokes equation. Navier-Stokes equation is what is the governing equation. So here, inviscid potential flow is Euler's equation. Euler's equation. We have discussed all these things yesterday. So then we discussed about compressible, incompressible flows, incompressible and compressible flows. Based on Mach number, less than 0.3, if you can have a first approximate calculation and see that the Mach number is less than 0.3, you can always go for incompressible flow equations. And you see that Mach number greater than 0.3, you can go for compressible set of equations to define your problem. Okay. So, and then another classification I told you is about steady, unsteady. Okay. Steady or unsteady flow. So here I told you, if you are trying to understand uh, the flow physics in terms of time domain, so you're tracking the properties of flow physics in terms of time domain. You see that you can, let's say I am tracking pressure of a particular point in the fluid domain against time. Okay, and I'm getting some information like okay something like this. So which means that the property I'm tracking against time is always varying with respect to time. Such physics is called as unsteady because always there is a component of the variation of the property with respect to time, and this is not equal to 0. Okay, you have always a value for this particular change in parameter. Okay, so over time, the fluid physics is varying its property. So such flows are called as unsteady flows. Okay, such flows are called as unsteady flows. So on the other hand, if you track some fluid physics, you can see that over time t, uh, you are tracking some property, and you see that there is no variation over time. Such physics is called as steady flow. Such so you can have steady flow physics to define your problem. Okay, so I will give you an example for such things. So, for example, you have a problem. For example, you have a problem of a flow over a aerofoil. Okay, you have a problem of a flow over an aerofoil. Okay, the flow is approaching the aerofoil. It sees the body, takes the route. Okay, so it goes very smoothly over the body. It goes over the body, streamline goes over the body without any disturbance. So here you have a solid body. So I have kept a probe. I have kept a probe in the region. This is a pressure measuring probe. This is a pressure measuring probe. Okay. I have connected this pressure measuring probe to a graph plotter. Okay, which is giving indication of the pressure against time t. And this is a probe which I have kept in the field. This is a probe. Okay, and this portion of the flow is called as free stream. Okay, so because it doesn't see the presence of the object in the field, so it is called as free stream, undisturbed flow field. And behind the body, you have a point called as wake. So this is wake region. Okay, so or it is also called as downstream flow region. Okay, upstream flow region and downstream flow region. So now the probe measures an indication, and see for this sort of flow, I have a measurement, something which is nearly over time. It doesn't vary over time t. So this is one particular case when which I have a steady flow. Okay. So if I expect the flow to be like this, when I try to model this in CFD software, or if I try to write a code, so I will go with a laminar steady flow solver. Okay. So I know this is going to be sheet-like flow, laminar flow, and it is going to be steady over time t. This is what I expect, because some intuition on the physics and my literature knowledge, the way I have read the literature on such flows, gives me an indication that the flow is going to be steady and there is no flow separation, because we have some information on the characteristics of the lift against angle of attack for aerofoils. Okay, so we have experimental information available, and you see that flow separation can happen only after some region angle of attack, which is called as stalling angle of attack. Okay, so this information is already available with me as an computational scientist. So I know that this angle of attack is not very large. It is a very smooth aerofoil, and there is no chance of flow separation. And I can always go for a laminar steady flow simulation in this case. So I'm just changing the plate now. I'm just changing my field of study now. I'm going to see how the flow field would be with a higher angle of attack. So when I mean angle of attack, it says that so the tip to code, and the free stream direction. So this is angle of attack. Okay. So a line connecting tip to code with the free stream velocity direction. This is angle of attack. So at a higher angle of attack, say something like around 10 degrees or something like that. So the aerofoil still sees the flow, and there is a flow separation point. Okay. And here, the flow is something like this. And this is aerofoil at a higher angle of attack. This is free stream region. Okay. Now, here I have a region where the flow has separated. The flow has separated because it, I'll explain. So now the flow, there is a recirculation region because there is some fluid which cannot go anywhere, but it has to rotate this region. This is known as recirculation zone. Okay, this is the separation point, flow separation point. Now you see that the wake region here has got recirculation zones, or the presence of eddies. It is called as recirculating regions, which is transported in the wake region. It's called as eddies. Okay, small elemental rotating fluid particles within the wake region is called as eddies. So now you have a presence of eddies. which are periodically shed behind the aerofoil. So again, if I am trying to keep the same probe, if I am trying to keep the same probe of for measurement here, and this probe is connected to a pressure sensor, again, I am trying to plot the pressure variation, okay, against time t. Now I can see the pressure is going to vary haphazardly against a mean point, okay, because there is a flow separation region. There are recirculating uh, small eddies or what is present in that region, this wake region, and it is being carried away, transported by the advecting fluid. So now you see that the pressure probe always senses a signal which is varying over time t. So why I told you is that now the first one being a steady flow, where you used a laminar steady flow approximation for simulation. Here, the same condition does not apply because it's the same aerofoil but at a different angle of attack, And see, suddenly the entire physics changed, and you cannot use the same set of equation to model in CFD the flow over a aerofoil at a higher angle of attack. This is true for all physics. Okay, when you change the parameters, you should also expect the flow physics will also change, and the different set of equations would have to be solved. So now here you have to go for turbulent, unsteady flow equations. So see the difference here. Here you are trying to solve a laminar steady flow equations. Here in this physics, you have to solve a completely different set of equations, which is turbulent unsteady flow equations. So what I am trying to tell you is that don't be don't fix your thoughts that okay, I have an aerofoil, I have an flow approaching it. It is always going to give a same type of physics. No, as you change the parameters, a completely different set of physics can dictate the flow field, and it's a completely different set of equations would be required to give you the correct answer. Okay, so how to know which is the set of equations that to use, which is the type of flow field equations I have to select for my computations. For this, extensive knowledge on literature on similar, or you may not get the same problem, but you can read on similar problems. You can get information from different literature, and you can apply suitably for your programming or your modeling in a software which is commercially available. Also, a large part of your intuition will also help you in defining the flow physics. So most of the physicists or most of the fluid physicists were highly intuitive. Okay, more than mathematical acumen, they were intuitive. I will give you an example. Ludwig Prandtl, okay, Ludwig Prandtl, who gave the most famous boundary layer theory, he was not a mathematician. He was a physicist of great intuition. Okay, he could visualize things. He could visualize many things which mathematicians could not. Okay, most of his students were good mathematicians. Most of his PhD students were very good mathematicians. So what he thought by intuition, his students could convert into mathematical solutions. For example, you may have heard Blasius, who was a student of Ludwig Prandtl. So whatever physical theory that Prandtl proposed and gave experimental evidence, Blasius gave very closed form solutions or very easy analytical solutions because Blasius was a good mathematician, which Prandtl was not. Okay, but sometimes a good physicist is also a good mathematician, just like von Karman. Okay, who has devised so many things in supersonic flow physics, von Karman, and so much of mathematical techniques also in fluid physics, von Karman integrals. So such rare genius who is both good physicist and good mathematician would come once in a while. But most of the times, a good fluid physicist is a good intuitive person. Okay. So whenever you try to devise a CFD solution, please be intuitive. Okay. So there is no hard and fast rules that all the physics should be the same. Fine. So now, so having said that, let's move on to the different governing equations and the different ways in which the governing equations could be written. So yesterday we were trying to understand the governing equations. Okay, so the G is what we call uh, in the. So I told you the governing equations could be in the form. Yesterday we discussed in the form either in non-conservative form, in the non-conservative form, or in the conservative form. Okay. So I told you the governing equations could be in the form of non-conservative nature or conservative nature. And I told you yesterday what is meant by conservation and what is meant by non-conservation. Okay. So we discussed about the flux being a part or the divergence theorem coming into the derivation or the control volume approach coming into the derivation of the governing equations, which inherently makes it conservative because you are talking about what happened with a physical quantity. For example, what happened with mass flux, what happened with momentum flux, what happened with energy. So there was a collective combination of terms which is going to be tracked, okay, or conserved. This is why such equations are known as conservative equations. And if you want to take a differential form of that equation, and you see that all the terms which represented the physics came inside the bracket of the derivative. They were not standalone. Okay, so there is a meaning. You are tracking the change of a physical quantity over time t, over different spatially or temporally. You are tracking the change of a physical quantity. So always when you look at the equation, and the equation is of the form of tracking the change of a physical quantity, that is a conservative form. Now I also yesterday explained you can take you can elaborate or expand the differential terms in individual variables in the form of individual variables. Now suddenly for a mathematician, it doesn't make any sense. It doesn't make any difference that whether the terms are collectively represented inside the bracket or they are represented individually out of the bracket. For example, we discussed about. So, for example, we discussed about the governing equations, mass conservation equation. Okay, starting with control volume approach, mass conservation equation, control volume approach, which was a conservative form. We obtained the differential form of equations as dou rho by dou t plus the divergence of the mass flux is equal to 0. So here I told you what is here. I told you this is tracking kilogram per meter cube into meter per second, and this is effectively kilogram per meter square per second. And I told you a quantity which is crossing unit area over unit time is called as flux. Okay, and this is representing mass flux because the quantity which is crossing unit area over unit time is kilogram or mass. So this form of equation, it is actually clubbing together the mass flux inside a common bracket, which means that you are tracking the change spatially for the mass flux. So basically, this is a conservative approach because all the quantities are clubbed together and you know what you're tracking. So I told you, it can also be written mathematically. It is also correct to write the expanded form of this equation with further expansion, which is the velocity dot, the gradient of density plus density into divergence of velocity. This is the expansion for the terms in the bracket. Okay, the terms in the bracket. And on the right hand side, you have 0. Okay, suddenly you see that you lost the physical meaning. You lost the physical meaning of this set of equation. Okay, now this says that divergence of velocity. This part it says divergence of velocity. So what is divergence of velocity? It doesn't make any sense to me physically to explain it. If it was divergence of mass flux, I know mass flux is crossing unit area. So I have an area. I can visualize something like this. Okay. If it was this, okay, if it was this term, I could visualize. there is a normal vector, and there is an elementary area, and there is some velocity vector which is pointing some direction. Okay, and some quantity which is representing kilograms, okay, per meter square per second is crossing this unit area. Some mass is crossing this unit area per second. This is what I could understand physically if it was written in this form. But when I write in this form, divergence of velocity, it doesn't make any sense to me. So for example, so divergence of velocity, if I expand, it says that one part is this, which means that, so meter per second over meter, this is nothing but 1/second. What does 1/second mean to me? I don't know what is it. Okay. So the physical information is lost now. So exactly, this is the problem with non-conservative form of equation. You don't know what you are tracking. Okay. It is mathematically correct to write this. Okay. For a mathematician, it is not different from this form or this form. But for a physicist, it makes a lot of difference in visualizing the things. Okay. So this is what where we left yesterday. The flow of equations can be written either in the form of conservative or non-conservative form. Okay. So I hope everybody is in the same page. We understood all these things. Okay. So, and I told you the derivation came from control volume approach, the conservative form of equations. The derivations usually come from the control volume approach, where you have a fixed region of space and you're allowing the fluid to pass through the fixed region of space. Okay. Now, let me, before going into further details, let me ask you one thing. Are you all very eager to use the software at this point now? Or is it okay that I explain the physics before using the software?
Sir, you can explain the physics before you can start using the software.
Okay. Okay. So the software we can always go into. Even somebody says that software is required now. Okay. Um, so to satisfy the people who really want to go into the software, I can go with the software tomorrow. Okay. I have that software installed on my computer. I can do that. Okay. So today, let me proceed with what I was trying to tell you. So here again. Okay. 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 So let me. So now we were discussing about how different the control mass and control volume approaches were. So two different approaches in writing the fluid physics we were discussing about. So Hari, can you please mute your Hari Shankar? So here I was telling in control mass approach, the Newton's law is enough. Okay, Newton's law is enough to detail the flow field. So here you have a position vector. Here you have a mass. So the particles are considered to be discrete control masses, and you have a particular velocity, which is dictated by the change in position. Okay, in a framework, the framework can be a fixed one, a moving one, whatever it is, in a coordinate system, and the acceleration can also be. I'm sorry, guys. God. So here you have. So for the people who are really interested in software, I'll come to that. Okay, because there were so many levels we can go through for CFD. If you are really patient, we can go very peacefully through all the different levels. Okay, so this particular level one is not a one-stop solution for all your needs. It has we have to be very patient. Okay, but still, I can do that for you. And also, I was telling this is a framework. And here, acceleration at any point can be the change of velocity with respect to time t. It can be the second derivative of time, space with respect to time. So this is for control mass approach. So here, the techniques could be Rangakuta method, to track the different positions and all. You can use higher order Rangakuta method in CFD. Okay, you can see that. So there are so many types of methods you can use for updating the position in control mass approach. In control volume approach, on the other hand, you have a field. You have a control volume. Okay, have a control volume. You have a control volume. So let me say this is the control volume. And these are control surfaces. This is called control surface 1, control surface 2. So the surfaces which make up the control volume is called as control surfaces. Okay. And you are here you are tracking the flow of particles and you are moving along with the particles. Here you have just kept your uh, uh, area of observation very fixed, and it is this fixed region of space can be real or imaginary in the domain. You are looking at that particular location only, and you are seeing what happened with the flow that is entering this control surface, what happens with entering the control surface from different directions, what happens with the flow that is leaving the control surfaces to the different directions. So this is your concern. You are not concerned about individual fluid particles. So in this particular type of approach, okay, in this particular type of approach, let us take a particular location here, okay? And the property at this location I am interested is, let me say it is a scalar. Uh, when I say scalar, velocity being having it's varying with respect to x. Okay, and here if you see, velocity is having different components, scalar components. Okay, so how would I read it? I would read that velocity is a function of position and time, and velocity has components u, v, and w in different directions. U, v, and w being small letters. Okay, and since velocity is a positional function and time, each of its component is a function of position and time. So there is no doubt about it. Okay. Similarly, you can write all the individual scalars being a function of space and time. Okay. So I'm just for the simplicity, I will represent only one particular point. Okay. So here I have x, y. Is it? Okay. And this is my control volume. And say this is the point at which I'm having a probe, pressure measuring probe. Similarly, I have another point here. Again, I want to track u at this point. Let me say it is u1 and this is u2, two different points in the field. Okay. So now there is no control mass. I have only region of space. I am taking reading. Okay. I am taking reading at these two positions of the velocity, flow velocity. So again, you know that this is a function of space and time. Okay. Which means that basically any scalar is going to be a function of space and time. Okay. So now I want to track the complete change of the property of the scalar, which I call as the derivative over time t. Okay. Okay. So this being a function of space and time, I can expand this on chain rule. I can expand this term on chain rule. First by doing this, the partial derivative of this scalar with respect to time t, and how the variable itself would vary with respect to time t, which is dt by dt. Now, how the property would vary with respect to space, and how space would vary with respect to time. So this is nothing. It is a basic chain rule I'm trying to use. It's a mathematical technique when you have a particular scalar being dependent on, if you have a variable which is dependent on other variables, how that variable, the change in the variable would be affected. Okay, this is what I am trying to tell you. It is not nothing new. I need the space, so I'm erasing it. Okay, plus now you have the change of the property with respect to y and the change of y with respect to time t. So I'll come to that. I'll come to each of the terms. Okay, and then so here one is capital D, one is small letter d, and another one is dou. Okay, so this is d and this is dou. Okay, please note this, and this is called as the total derivative. This can also be in some textbooks, it can also be written as capital D, small d or capital D, both are the same. It is called as total derivative. And here you have small the dou, which you dau dou, which is called as a partial derivative. So while taking partial derivative, you are only concerned about uh, the change of that property with respect to a particular variable alone, keeping all the other parameters the same. This is what you mean by partial derivative. When you conduct an experiment, if you want to track, if you want to know how one parameter would change with respect to another parameter while keeping all the other parameters the same, okay, you have, let's say, your you are trying to boil water in a kettle. You are trying to boil water in a kettle in ambient conditions. You are trying to provide energy in the form of a flame which is heating up the fluid, and the fluid is kept open in ambient conditions. And you know that the boiling temperature, the temperature at which boiling happens or the bubbles form, you know, the physical visualization of boiling happens is dependent upon the ambient pressure as well as the energy or the temperature rise you give. So two parameters immediately come to your mind which can affect boiling point. One is the heat that you have provided in terms of delta T, as well as the ambient pressure that you have set around the fluid which is trying to boil. Okay. So if you want to try to understand uh, how energy, the heat provided alone influences boiling, then you have to keep the pressure the same. Okay. Or in other words, if you want to find how pressure, atmospheric pressure affects boiling, then you have to keep the how pressure variation affects boiling, then you have to keep the temperature same and vary pressure. You see, this is exactly what we are trying to see here. So partial derivative exactly tells you that whenever a property is influenced by multitude of properties, if you want to track the change of a variation of a property with respect to another property, you have to keep hold of all the other properties the same. This is what exactly is done here in taking while taking partial derivative. Okay. But total derivative permits you the complete variation of all the physical properties which can influence physics. So that is why it is called as total derivative. Okay. So here, so here, uh, when I am trying to say acceleration, acceleration, okay, I am mentioning about the total change of the scalar over time t. And the scalar itself is a function of multitude of independent variables x, y, z, and t. Then I have to individually track how they would vary with respect to the individual variables, okay, in collection. So this is why we are using chain rule. So mathematics permits us to do you use chain rule, and we get this form of equation. So there is a reason why I am trying to explain this equation for you, because it's very important to understand this in understanding many of the things that will come later. Okay, so let us look one by one all these terms du by dt. Let me write this. The acceleration which I was trying to find, acceleration of a particular uh, acceleration is also another field. Okay, now velocity is like the velocity is distributed in this domain, so I called velocity field. Similarly, acceleration is also distributed in this domain, so I can say acceleration field. So the acceleration of the fluid at that particular location is dou by dou t into dt by dt is 1. So I need not write this because this is equal to 1. So now again dou u by dou x is here and dx by dt. Be very careful when you watch this. Uh, I am going to write first dou u by dou x, which is already there. Okay. And here it says dx by dt. Dx by dt. It doesn't make any sense to me initially to do something like that because here I am having control volume approach. I don't have a control mass which is moving. And still, it is asking me to perform an operation which is change of position with respect to time. Change of whose position with respect to time? I don't know. Change of whose position with respect to time. Then I think about enclosing this region. Okay. Then I think there is a possibility I can find that. Okay. Mathematically, it should be able to be found because that is how the equation is. So I should be able to find that. So I am going to subdivide the domain into smaller sections. Okay. So now, while dividing this control volume into smaller control volumes, while dividing this control volume into smaller control volumes, by performing this operation very carefully, I see, I see there is a possibility I can find this. I see there is a possibility I can find this because now I have a small control volume. So because there is no fixed limit for a control volume, only concept of continuum should be satisfied. That's all the we have to be careful about. Okay, it can be big control, it can be elementary control volume, all are control volumes. Now, when I see this elementary control volume, I see that there is a possibility I can evaluate dx by dt because this control volume now looks like to me a control mass. Now it looks like to me a control mass. Okay, exactly now I know it is asking me to track what happened with the control mass when it is passing this location of control volume. See, now on the derivative or the differential level deep into the equation, actually a control volume approach is a control mass approach. This is exactly the physics or the fundamental behind Reynolds transport theorem. Okay, in fluid physics you learn RTT or Reynolds transport theorem. It is just a chain or connect between control volume approach to control mass approach. Deep down in the equations, you are actually modeling control mass approach in control volume. Okay. So now I am very happy I can find dx by dt because I know whose dx by dt we are talking about. Okay. Now I can assign. I'm really happy that I could get that because I know exactly whose, and I know dx by dt for this. So this dx by dt, I understand that this dx by dt is of this elementary control mass which is concentrated in this location, and I can find that as the velocity. So I can substitute the velocity at that point in the field to be u in this equation. Okay. Similarly, I can go with the other things. You see here, dy by dt appears, du by dx appears. So here I know that we are talking about v at that particular location. So I can substitute v and the other things appear automatically. Okay. Automatically comes into picture. So this was my only doubt, which is now clear when I try to connect control volume approach with control mass approach. And this is the essence. I will not write this is Reynolds transport theorem because Reynolds transport theorem has its own derivation, but this is the essence of Reynolds transport theorem. We can connect CV connected with control mass deep down in the differential or elementary level. Okay. So now you see that. So this is not exactly what I wanted to tell you. So So you might be thinking that I'm taking you far away from what you really wanted from me, but please understand this is also required. If you want, I can explain further. So now I get. So here, so I told you this is what we are tracking. Okay, let me. So I have got something like this. Okay. Okay. This is the expansion I got for the. So here it says the total derivative, total change you can call total derivative of any property. Let total derivative of any property is equal. So this part is called as time derivative or temporal derivative or local derivative. Local derivative of that property plus this part you can club together as divergence of velocity. Sorry, V dot grad V. Okay. Uh, grad V. Okay. So the local derivative, which is dou u by dou t, plus the velocity dot grad v. So let us try to understand. Velocity is nothing but field function is nothing but ui plus bj plus wk, and gradient operation performed on a scalar u is nothing but dou u by dou x I plus dou u by dou y j plus dou u by dou z k. So you see that these terms would be multiplied together because these are the terms which are on the respective unit vectors are the same. When you take the dot product, it would appear exactly. It will give all the components. So basically, you can write v dot grad u to be this part, the parts in the bracket, and this part is called as convective derivative. So you see here, you have, if you want to track the total change, you have to first find the local change plus convective derivative. Okay. So physically, it doesn't talk about space. The first one doesn't talk about space. This part doesn't talk about space. Okay. It is, you are tracking the change in time alone. Okay. You are tracking the change in time alone. So can somebody tell me, if I want to track the change in time alone, how I should set my probe for measurement in a flow field? Anybody?
Sir, can you repeat what did you ask just now, sir?
Okay. I am trying to make you think how how these quantities which I have written in equation physically makes sense to you. I was asking you, if I want to track the change of a property in time alone, how the measurement setup should be located.
In a fixed position.
Exactly. Very good, Amarnath. So here it means that the probe cannot move because I'm not taking measurement at different locations. I am going to take the measurement at a particular location, and this value information which I am tracking to see is only varying with respect to time, which means that the probe should be fixed at a locality. This is exactly why that derivative is called as local derivative. You are tracking the change of a property at a particular locality without moving. What about the other part? What about the other part? What does it tell you? If you want to track the change, what you have to do?
Move through the field.
Yes, you have to move through the field. You have to travel through the field. You have to take one value measurement of you at a particular position X. You have to move to another position, take another measurement of you at that location. Then you have to compare the change of that value with the another value spatially. You have to compare in spatial domain how this varied. Then this will give you the spatial component of variation. This is why it is called as convective derivative. The change happened with tracking the flow in space, or you moved along with the flow. This part of the change happened because the flow convected or it traveled through the space. Okay. So one property. So when you are tracking the variation of a property, the total change in the property, that change is affected by local variations as well as due to the physical motion of the fluid being transported in the space. Okay. So this is exactly why it has got two different components. And this is very important to know that all scalars that is being transported in fluid physics can be written in the same equation form. Okay. Okay. You can, without worrying, you can write the total change of any scalar, which I commonly call as B, the total change. It can be dB by dt, capital letter or small letter dB by small letter dt, whichever way you want to write. Okay, both are the same. Okay, this is equal. It will have a local derivative part. Okay, the scalar. I'll say that it's generic scalar. Okay, so please let me know if you want to leave. I can stop midway. No problem. A generic scalar. It can be a temperature. It can be pressure. Whatever. Okay, which you're trying. It will have a local derivative, and it will have a convective derivative. So see, such a simple equation came out of nowhere. Okay, just when you try to relate the physics of fluid, we got a very simple mathematical equation which you can use for the transport of any generic scalar through the flow field, which is a very important finding. It makes a lot of things easier. When you try to relate fluid physics, it makes a lot of things easier because for any scalar, this is applicable. This is what I'm trying to tell you. So see, the scalar can be pressure, the scalar can be temperature, the scalar can be the momentum, the scalar can be mass itself, where you saw the mass conservation equations in that form. So many possibilities you can write this. Okay, any of this. So why did I tell you? I told you this because you got the mass conservation equation in this form, in conservative form. You got this. This is what you got. And on expanding the second part, this being the same, This is what is the expanded form. Okay. So now this is the expanded form. This part is expanded to this. Okay. Now let me write. I'll take another color. So you observe this part. What does it appear to you? It has a local derivative. It has a local derivative of density. It has got a convective derivative of density again. Here density being the scalar. Okay. Now plus this part, which comes from expansion. Okay. So this collectively you can write as what you can write? You can write as d rho by d. The total change of density plus this part, which comes from okay. So now this is the form of conservation of mass, okay, which includes the total derivative of density included. Okay. So here, so this is what I was trying to tell you. You can include the total derivative concept in conservation law. Okay, the total derivative concept of a scalar in conservation law appropriately. Now you see how the equation looks like, including the total derivative. Okay, here there was no total derivative here. On expanding it further, you included total derivative concept in conservation law. Okay, this is very important. Okay, this is very important because the convection diffusion equation, which I will later tell you, on which you can use the different numerical schemes which you see in the commercial solvers, actually follows this principle in establishing relation or the profile assumptions for different flow physics across control volume. So if you want to understand that, you have to understand this. This is why I told you the conservation laws can include the total derivative concept while elaborating the equation. Okay. Okay, fine. So can anybody tell me, is the form which I wrote here conservative or non-conservative? Can anybody tell me?
Non-conservative, sir.
Sorry.
Non-conservative.
Yes, it is non-conservative form. The form of equation which I included total derivative concept into the conservation laws is actually giving me a non-conservative form of governing equation. Okay, the same equation you can obtain from control mass approach. Okay, so on looking at an equation, you should be able to tell whether it is a conservative form, non-conservative form, or what sort of type of equation it is. Have they followed a control volume approach, control mass approach? Is it eligible to be applied for CFD code, or is it not? Is there any difference in using this sort set of equations for your problem or not? Okay, this sort of equations is good for incompressible flows, but if you try to use the same set of equations what I present here for compressible flows, you'll get uh, completely wrong results. Okay. So I'll take 5 minutes of your time to explain another thing because tomorrow I may need the expansion of convection diffusion sort of equations. For that, I would just give you. So if you can be patient for another 5 minutes, I hope we can cover this also. So now the second set of governing equations is conservation of momentum. So we learned many things. We learned how conservative, non-conservative forms can be written, how total derivative concept can be included in writing governing law equations, governing equations, and when they appear in the equation, what sort of nature of the equation it becomes. Okay. can they be used for incompressible flow simulations or compressible flow simulation? We discussed so many things. So now conservation of momentum. So let us follow another concept. Okay, let us follow another concept where I am trying to move along with the control mass. Okay, the control mass approach is taken here. So I was telling you can follow either control volume or control mass approach in detailing the physics. Okay, let me say that this is the path in which the fluid element is moving. I am just taking one fluid element to find the control conservation of mass. Okay, so it is a fluid element, uh, conservation of momentum, which I call as Newton's law, which is giving me force is nothing but mass into acceleration. I should be able to write this for this fluid mass, fluid element. So let me say I want to track only the change or the net force in the x direction. Okay, so I need that coordinate system. So this can be done in all the different directions. So I don't want to elaborate so much because the same set of equations will repeat for other coordinate axes. So here it would be mean I have to track the mass and I have to so the mass is not changing, it's a control mass, and acceleration of the element control mass has to be tracked. And this will give you net force that is affecting on. So here, so in order to understand this things very clearly, let me redraw this fluid element. Okay? Let me redraw this fluid element. So please be careful. I'm following controls mass approach now. Control volume, not control volume approach. So I'm not drawing a control volume. I'm drawing a fluid element. Please be clear. Fluid element in motion. So by following this approach, I should get non-conservative form of equation because I am following conservative control mass. So here I have coordinate axis x, y. Okay. So I have 6 different faces for this cube-shaped fluid element, and I am tracking mass into acceleration to find the net force which is trying to move this fluid element because that is momentum. Okay, mass into forces mass into acceleration. Okay, so momentum would be mass into velocity, which is effectively the change of velocity over time, t, which will give me acceleration. Okay, it's all leading to the same point. Okay. So in order to understand the net force, I told you there are different types of forces which can move this element. One being surface force. Surface forces can be a reason to accelerate this element. Also, I told you there is another type of force which can move this element, which is body force. So a combination of surface force and body forces can create this acceleration. So first I understand what are the different forces which can create acceleration to this fluid element. And I know that in fluid physics, surface forces and body forces are going to move this fluid element. So I am trying to understand where these forces are located in order that this motion is possible. So I see that surface force is possible here. Please feel free to leave. Okay, if you want to leave, I'm not stopping you. Okay, the surface forces can act here. So this is the starting, and this is why I drew like this arrow markers like this on this surface, and the bottom surface a resistance, because we have discussed this concept of viscosity earlier. So I'll draw like that. Okay. So some convention is required for me to draw. This is why I'm following this. Okay. We can follow different conventions. So I have to draw again. It's very difficult to draw this. I tried different applications, but still not one note is better for me. So here on this face, the surface force would be something like this point. And on this force, These are basically called as shear forces. As you see that surface forces are called as shear forces, which are tangential. Okay. So similarly, you can see on the other side something like this. On this side something like this. Okay. So I think I feel that you can visualize what I have tried to draw. These are all acting on the faces. Okay. And I call them shear force. Okay. And another type of surface force can be normal force, as I told you. So the surface forces can be shear and they can be normal. And body forces can be gravitational. It can be magnetic field force. So many examples. Okay. So now another surface force is this one, the normal force, which is acting on the face, which is trying to pull this. Okay. Okay. Now with surface forces, there is always a sign convention that is associated. If you want to represent surface force with respect to stress, okay, if you want to write surface force with respect to stress, you can write as stress into area. So this is how you write force. Force is nothing but the product of surface stress into area. So here you are mentioning about surface forces. You have a definite area on which the force is acting. So you already know what is the area. And this is what is of your interest, the stress. Okay, very important, stress. So here, let me draw with another color. So this is the dx, the height of the fluid. Sorry, I'm really sorry. Dy, the height of the fluid element. This is dx, the width of the fluid element. And this is the thickness dz of the fluid element. Okay, let it be so. Okay, so I have different surfaces according to dx, dy. I can calculate the area on which it is acting. Okay. Okay. So now here I am interested into identifying the stress acting on the face of the fluid element. I am interested to see what this means. Okay. I am interested to see this because I know area. I told you, because if you have a dx, dy, dz available to you from the width of the different geometrical thickness of the fluid element, I can easily calculate either it is dx into dy or dx into dz or dy into dz. It is calculatable. So this is of my interest. Tau is of my interest. If I know this, it is easily solvable. So how to calculate that? I'll erase this for your convenience. I'll erase this. There is always a sign convention associated with writing stress. Okay. So this means stress, the stress along j direction. This always means stress along exerted in a plane perpendicular to I direction. Okay. Okay. So here, this is called as Einstein notation. Okay, you can go on changing cyclically the ij values, ijk, jk. You can just go on cyclically changing the notations which appear on the suffix. This is called as Einstein notation, because with the same notation, you can represent even tensors. You can represent a large set of values which will follow cyclic order of information. So here, following this notation, the notation stress ij would automatically mean I am trying to express some stress along j direction. Okay, you see the position of ij in j along j direction exerted in a plane perpendicular to I direction. So you see that if I want to write something, if I am writing something like tau xy, automatically it means I am calculating the stress, indicating a stress which is in y direction, and the stress will appear in a plane that is perpendicular to the axis which is x. So how it would look like? How it would look like here? Okay. So here uh, it is in the direction y. So here I have. So let me redraw this coordinate system for your convenience. Because I have limited space available here. Okay. So I may. So it says that I have to track the variation. I have to find a stress which is along y direction. So this is y direction. So this is stress is going to appear in this direction, and this is perpendicular to uh, x direction. The plane on which this is acting is perpendicular to x direction. So here it would mean the plane. Sorry, I have to draw with another color. Sorry. Which means that the plane on which it is acting should be something like this. Okay, the plane on which it is acting should be something like this. Then only it is true. The stress is going to act in the y direction. Stress is going to act in the y direction. So one thing is okay. And the plane on which it is acting is perpendicular because this plane, through this plane, the perpendicular x direction is passing. So this is the plane. So in this picture, this is that stress I'm talking about. So xy. Okay. Similarly, you can go on finding the other planes. Okay. What happens with this? What happens? You can go on finding on your own. Okay. So I will just explain one. You should follow this notation. So let me give another. I hope it is clear. Is it clear? Are you all there?
Yes, sir.
Yes, sir.
Okay. I hope it is clear. I'll wind up just now in within 5 minutes. Don't worry. So if it is xx, okay, which is the so this is shear stress. Now this is normal stress. The both of this we are interested to find. Okay. So it is according to this notation, this has to act in the x direction, and the plane on which it is acting is also perpendicular to x direction. So it has to act along x direction, and the plane on which it is acting should be perpendicular. So again, this is the plane we are talking about, the same plane, but the direction would be this one, tau xx. See, tau xy on the plane. So this is normal and this is shear. So likewise, you can locate all the shear stresses, and once you can locate the shear stress, you can calculate the accordingly the force which is acting in the x direction, the force which is acting in the y direction. Sorry, x direction force by acting in the y direction, or the force acting in the z direction. We can appropriately find. So I'll wind up today's class for today. I hope it was informative for you. Tomorrow, let's see some software part of it to help people who are really interested to see what happens with software and all. Let's, but this is not the time I can move on to it. But still, for them not to feel left out, I can go into the software part of it. So is it okay for today? I hope it is informative.
Sir, which software are you using for the CFD?
Okay. You don't please worry about what software you are going to use for CFD, because different softwares it will have its own learning process or learning curve involved. I'll be using Fluent to explain some concepts because I am familiar with Fluent. Okay. So let me explain some concepts with Fluent, but we have not come to a stage where we can come. So this is what I was trying to tell you. We have to be very patient with learning CFD. Okay. CFD is CFD. Computational fluid dynamics is computational fluid dynamics. You have to first understand what is fluid dynamics, then only you can compute fluid dynamics. So most people are really interested to use the software in a hurry, and because of which, uh, are they really using CFD? We don't know. They themselves don't know. This is why with this lecture series, I really want you to take and benefit from whatever small little things I know, so that you can really use CFD for your application. Ultimately, nobody can teach you anything. For a specific problem, you really have to invest your time and energy and your intuition in detailing the physics of the problem on your own. But the background knowledge, the foundation will definitely help you in detailing that. So, so this is why the background knowledge I am trying to provide you with some knowledge on this software for level 1. It will not be the same in level 2 or level 3 or intermediate level, because we will mix many things. We will mix the software, we will mix the information that is available. So you think about it, okay, which is good for you. Because if you want to build a house, you have to make a foundation clear. Okay, this is what we are trying to do now. So you please think about it. Are you really in a hurry to learn CFD, or you can peacefully learn CFD so you please think about it. Okay. I normally am not very in a hurry mood to learn anything, because I usually take it. Things have to be learned means they have to be learned the way it is learned. Okay, this is how I see things. So please have a retrospective thought process within yourself and decide what you really want. Because I want to deliver the content in a particular fashion. Is this okay? You have to think about it. Okay.
Yes, sir. Your class is so very informative. Sir, we want to learn more and more. We want to get more and more information from you, sir, so that we can really understand CFD.
So in that case, you have to be really patient. I demand only patience from you.
We have
Okay.
no help, I think.
Yes, there is no hard and fast rule for learning things. We have to be very patient. That's all. So I guarantee you, if you go through a rigorous course like this, step by step, I can be your teacher. Somebody else can be your teacher. Anybody can be your teacher. Uh, so I'm not saying that I am the ultimate guru. No, I'm saying that I can give some information which can make foundations to you, so you can learn on your own later. Okay, but I see that this has to go step by step. Is it okay?
Yes, sir.
Okay, thank you guys. We'll continue the class next time with some more topics which can be somewhat informative to you. Thank you everybody for joining. Some near